Hey, chemistry people. It's time to start chapter 11. Some of you are kind of dragging your feet on the stuff that I've given you to do. Don't do that! Don't do that! You're in school. So get your work done. Some of you, I don't even know where you're at. Don't make me threaten you. I love you very much. And I love chemistry too. So I'm going to tackle section 1 here for states and state changes. I think the content here in this chapter is easier than it was in the last one, though I guess you guys are the ones that are going to decide on the truthfulness of that statement for yourself. So I'm going to run through these slides. If you picked up your packet, then you already have kind of the little version of this for section 1 and 2, at least the important pages. And right, we got a bunch of terms today, and we got some a couple of pictures that you need to pay attention to. So make sure that you take notes. Make sure you highlight some stuff. There's going to be at some point there's going to be a vocabulary quiz, and a lot of vocabulary comes from this section. Secondly, I will link I guess the quiz that I made up for this section. It's going to be on a Google Doc. So when you get it, I need you to do this. I need you to not type on my Google Doc. I need you to make a copy of the Google Doc for yourself, rename it, type your answers in, and then send that back to me. Okay, so I don't want you editing mine. I want you to make a copy of it for yourself, edit that, and then send your answers back. So that's going to be I think I'll put that link in the email, or I'll give you sharing permission with that document. All right, here we go. Section 1, states and state changes. Oh, bananas. Okay. You guys know what surface tension is? Can you give me an example of something you've seen surface tension where you've seen that? Maybe like a bug walking across the water or something like that. All right. So say it out loud so that somebody at the house can hear you say it. Hey, I'm doing chemistry. I'm defining surface tension in my own words. Surface tension is the tension of a surface. There we go. Or something like that. Yeah, whatever. What state of matter is associated with surface tension? Is it solid, liquid, or gas? What do you think? Hopefully you got that one right. If not, I'll be praying for you. Okay. Here's what we're trying to do in this first section. Relate the properties of a state to the energy content and particle arrangement of the state of matter. How fast is it going? What state should it be in? Second, oh, come on. I'm going to click on that and then do this. Explain forces and energy changes involving changes of state. And that's it. There we go. Those are 2 things we want to do. Okay, so hopefully this is review, because we did some of the states of matter stuff last year in physical science, and you've had it like 3 or 4 times in elementary school. Most substances can be in 3 states: solid, liquid, or gas. If we're in physics, we're going to have a couple more, but we'll stick with this right now. Chemistry is about what we can do kind of practically, not in a super duper lab. Solid particles are really not moving very much. They're just vibrating, and they're in some type of crystal structure or packed closely together. Solid particles can vibrate only in place and do not break away from their fixed positions, so there's not a whole lot of interacting that they can do. Only along their surface, like think of a cube, only along their surface can you actually get any kind of interaction going on with stuff that's outside to do chemical reactions. Or even changes of state, you've got to add a lot of energy, and the ones that are on the outside are the ones that are going to absorb the energy first. Solids also, as you know, have fixed volumes and shapes. So that's why we got platonic solids from geometry, not platonic liquids or platonic gases. It's platonic solids. And many solids have shapes that are and volumes that you can apply a formula to. Here's mercury in 3 different states. You have to cool mercury down quite a ways because it's liquid at room temperature. Remember, it's the only metal that's a liquid at room temperature. But you can get it cold enough so that it's closely packed, like this picture over here. And then if you warm it up, those pieces can slide around. You can kind of think of it like a bunch of ball bearings rolling around on the table. If you ever saw Terminator 2, they filmed the liquid metal portions of the video of the movie by having a hair dryer and blowing bits of mercury around all over the place. And then thirdly, you can heat it up, make it in a gas phase, and then zap it with electricity, and you can have a mercury light. That's pretty common, and it gives off a certain glow with the spectrum. It's a line emission spectrum that is easy to pick out. So the particles are pretty far apart. So close together, will be able to move around, and far apart and able to go wherever they want to. Liquids can slip past each other pretty easily. Have random arrangement and can move in a semi-random way. There's a thing called Brownian motion, where a guy, Mr. Brown, he noticed that the dust particles on the surface of the water were bouncing around, and he figured they must be actually, the water molecules must be moving. They do have enough energy in order to slip past each other, which allows them to flow. And they have a fixed volume. All right, there it is, fixed volume, but can flow to take the shape of the lower part of the container. Do a really good job of that. That's why it's really good to have a cup for water rather than pouring it in your hand. Liquid forces lead to surface wetting and capillary action, a couple of important properties of water. They wet surfaces. Now, how do they do that? Well, there's a stickiness to water and stickiness to liquids in general. Usually we do think of liquids as being sticky. Liquid particles can have what's called cohesion. They stick to each other, like water that sticks to water, like a water drop. And we can have water sticking to like the sides of your straw, or, ooh, look at that. Well, you can't really see that too well, but I can get it to climb up the wall there and stick to it and make it wet. And different liquids have different values for their cohesion and adhesion. So some of them are stickier than others. Mercury is an interesting one to do in a small tube. If you recall, when we've talked about thermometers before, the mercury thermometers have a way of the pressure pushes the mercury up the tube. Balance of cohesion and adhesion determines whether a liquid will wet a solid surface or whether it will rather stick to itself. And water is a nice, sweet kind of medium. It does stick to both itself pretty well and to the walls of its container. Forces of adhesion and cohesion will pull water up a narrow glass tube. That is called capillary action. And I remember in chem lab in college, they had really, really skinny glass tubes that you could get things to go quite a bit up. It is one of the ways that that xylem works of pulling water up from the roots up into a tree. It's part of what helps the water transport from the roots to the leaves. It's capillary action. It's also what allows you to use like Bounty, the quicker picker upper, and you can dip your paper towel in there, and capillary action is what draws the water up up the paper. We are going to use capillary action later on in the chapter on solutions to pull apart the pigments of markers. Yeah, that's kind of actually pretty fun. You can actually pull the food coloring off of candy as well and split it out and see how many different food colorings they used. I'm going to skip to the next slide. Liquids have surface tension. Below the surface of a liquid, the particles are pulled equally in all directions by cohesive forces. However, surface particles are pulled only sideways and downward, so they have a net downward force. Have you guys ever seen slow-mo guys and how they slow-mo a drop of water hitting the surface and part of it breaking off and going into the surface and part of it bouncing? I should give you some bonus points if you watch that and do a write-up, maybe 2 paragraphs. Slow-mo guys, and they do a water drop in super slow motion, and it's pretty fascinating. It takes energy to oppose this net force and increase the surface area. The tendency of liquids to decrease surface area to the smallest possible size is surface tension. So the smaller the drop, the easier it is for it to stay as a drop. And then the more water, let's say, that there is, the harder it is for it to hold on to each other, and then it will probably pop. So we're going to have you do a little project this next week. Oh no, I guess Friday I'll send you a eyedropper, and we'll see how many drops of water you can get to stay on the top of a penny. I want you to think about whether a clean penny or a dirty penny is better. You can clean a penny by getting out some hot sauce. If you've got like a Taco Bell sauce packet, you can just put your penny in that and then wash it off, and then make sure you get a dirty one too. And we'll see if who can get the most water drops to sit on the top of a penny. Oh yeah. There was also, I think it was a objectivity video where they went into the archives of the science institution in England. I forget what it's called now. The Royal Institute. And there was a guy that did a bunch of pictures about what splashes look like and how they form those rings with little bubbles coming up and stuff. That's pretty cool because how's the guy like take pictures of that fast? He didn't have a slow-mo camera back in the 1800s. But did a lot of research in that. There's also some stuff about the Worthington drop. Smart Every Day called it the poop splash. So you might want to watch that about surface tension and the little vacuum, the little hole that it makes, and then how it fills that space back up. But there's some splashing going on there, and you can see some of that in slow motion. A very good thing for you to watch. Gas particles. Okay, solid, liquid, gas are essentially independent. They fly around. They don't have to interact with each other. They might not interact with each other very much because they're moving super fast and they're pretty far apart. Their attractive forces are not very big. They do not have a very big effect. In the next section, we'll look at different forces of attraction. Gases are so far apart, moving so fast, they really don't interact very much. They're more or less their own little particle. Shape, volume, and density of amount of gas change depending on the size and shape of the container. Just look around in your room. There's that much gas in the air. You can squeeze things down a little bit, like use a plunger thing. You can change the shape quite significantly, but you're going to change the pressure as you do that, and then it will change the density of your gas. We'll get to gases in, I think, chapter 13, maybe? Do gas laws. So there's our solid, liquid, gas, picture-wise, how they behave themselves. Let's move on to something else here. Changing states. Okay, now, I'm constantly amazed when I go over this how many kids can't remember what the things are called as things go back and forth between states. There's 3 states, and you can go either direction in that, so it's actually a permutation type of problem rather than a combination type of problem. Going from freezing to melting is different than going from melting to freezing. So there are 6, that is 3 factorial different ways that you can have a state change. And the little picture coming up next, you need to memorize. You need to know what it is called when you go from freezing to melting, or melting to freezing, or freezing to well, whatever. From solid to liquid, liquid to solid, all those. You're going to have to commit it to memory. We know that the temperature is one of the main factors, and the amount of energy that something is the main factor to determining what state something's going to be in. So adding energy, generally, we're going to go up the scale in phase changes here. We'll increase the substance temperature if you add energy, but at a certain point, you're going to get where the temperature will stay the same. And that is at a phase change. That's very important. We already talked about it in chapter 10, but when you go through a phase change, the temperature doesn't change. So we had a hard time using our formula for delta H. When we got to phase changes, we had to have another way of measuring that because it stays at the same temperature. So as water's boiling, the water's at 100 and the steam's at 100. And you get 2 phases there at the same time, but they're at the same temperature. Or if you're melting something, the ice is at 0 and the water that's melting is at 0. same temperature, even though you're adding energy to it to get more of the ice to turn into water. Muy importante. See? That means very important, Matthew. So this is the picture you need to memorize. You should practice it. You should draw it out on your paper. You can hit pause right now and do that. But you've got your solid to gas being sublimation. That would be like a mothball giving off gas. You could go from gas to a solid. And you got deposition. That would be like frost forming on your windshield in the morning. Like this morning was a pretty cold morning. You've got gas going down to a liquid. That's like when it condenses, you're warming something up and then it cools, hits a cool surface, and then it turns back into a liquid. You've got liquid to gas, that's evaporation. That's pretty normal. If you're in Miss Joseph's class, you remember the song. Liquid to gas is evaporation. It happens out there in the ocean. And then you got the solid to liquid changes. You got solid melts, becomes a liquid. Liquid freezes, becomes a solid. This one, you better not forget. It's these ones that you're going to be a little wonky on. So you need to memorize it. There's 6 of them because there's 3 states, and every state can go to every other state. Solid to gas, sublimation. Solid to liquid, melting. Liquid to solid, freezing. Liquid to gas, evaporation. Gas to solid, deposition. Gas to liquid, condensation. As the liquids evaporate to gas, they gain energy, then they're able to escape the surface of that liquid. They gain enough energy, they jump and join the gas particles. So evaporation is the change of state from liquid to gas. It is endothermic. It is something that you need to add heat to the problem for it to happen. Boiling point of is the temperature and pressure at which a liquid and gas are in equilibrium. And note that it says not just temperature, but also pressure. So you're going to watch a video later about how the boiling point changes at higher altitudes because the pressure is lower. Water boils at a lower temperature in Denver than it does down here in the valley. Gases condense to liquids. That's called condensation. They don't have enough energy, so they settle down and they slow down and stick closer to each other in the liquid state. That's an exothermic process. It gives off energy. Any change of state either picks up or drops off a certain amount of energy that is quantifiable. Condensation takes place on a cool night, causing water vapor to form dew. Solid melting to liquids. It's called melting. Change of state from solid to liquid is an endothermic process. Melting point is the temperature and pressure at which a solid becomes a liquid. If you squeeze something really hard, or you take a block of ice and you like pull a string on it really hard, you can get it to melt. How about ice skating? I'm gonna have you watch a video about ice skating as well. You got ice, the skate pushes down really hard, and there's a little layer of liquid that forms. At least that's one of the ideas. And then when the pressure is released, it freezes again. Liquid freezing to solid. Okay, freezing is exothermic. Freezing point is the temperature at which the substance freezes. This time it does not say pressure. And solid subliming. Super exciting stuff, isn't it? Change of state from solid to gas. It is endothermic. Gases deposit to solids. You can hit pause at any time. Molecules in a gaseous state become part of the surface of a crystal. When a substance changes state from a gas to a solid, the change is often called deposition. It gets deposited. It is exothermic. And that is the end of that section. Make sure that you review the stuff. Write down those definitions in your notes and check them. Go over them a few times before you go and do the quiz. Make it a quiz too. It's not like look it up in the book or have the book open and have my notes open while I do it. Study first, then take the quiz. And remember, I want you to make a copy of that document and then save it under your own name and then take it and then send it back to me. That's coming up, and that's gonna be due on Friday, please, because I got more stuff for you to do on Friday for Monday. Okay, I hope you're surviving, and wash your hands and stay away from people.